This video provides an introduction to stochastic programming with Recourse. Consider a linear program like the one shown here. The parameters might not be known fully at the time of planning, but will only be known at a later time when the solution is implemented in practice. If the problem has hard constraints that must be satisfied, an approach like robust optimization might be useful. This method takes the possible outcomes into account and finds a solution that satisfies all of them, meaning that it will provide a very conservative solution. The method is especially useful as well if no changes can be made to the solution after it is implemented. If the problem has soft constraints that are allowed to be violated, it could make sense to solve it using chance constraints. These allow the user to specify at what probability each of the constraints must be satisfied in the final solution. Whereas robust optimization finds a solution that is optimal in the worst case, stochastic programming seeks to find solutions that work well on average. This makes stochastic programming a natural fit for problems with soft constraints. Similarly to when using chance constraints, it is assumed that the distributions of each of the stochastic parameters are known. Typically, stochastic programming is used when some decisions can be postponed to a later time. This is referred to as stochastic programming with recourse. When recourse actions are available, it might be possible to handle hard constraints as well. As an example, consider the task of having to provide bus routes for the citizens in a city. The problem essentially consists of two subproblems. First, we have to decide how many buses to order. A specialized company produces these buses, and we can get a certain discount by buying many buses at an early time, well before any of the bus routes are implemented in practice. Obviously, the second subproblem is to plan the network of routes visiting key locations in the city. At the time we make the decision of how many buses we need to order, we might already want to consider what routes we want in the end. However, at this point, we probably only have an estimate of how many people will want to use the buses. When the new bus routes are implemented in practice, we will quickly get more statistics on the popularity of the routes. And at this point, we could change the routes, move buses from one route to another, or even add new routes or cancel routes to better match the demand of the citizens. This is one example of a recourse action. We are reasonably quickly able to change the route network, but we are limited by the number of buses we have. If we were to order more buses, we would have to wait for them to be produced, so for now we don't consider that a feasible recourse action. If the demand of the customers were considered hard constraints, i.e. there always has to be room in the buses for every customer, we might need other possible recourse actions. Perhaps we could rent buses from elsewhere to match the demand of the customers, hopefully with much shorter notice than having to wait for the production of more buses. But in the long run, renting is probably much more expensive than having the right number of buses in the first place. Stochastic programming with recourse can take these kinds of decisions into account when optimizing a problem. For an example like this, the optimal solution could be to order a few too many buses initially to avoid having to rent expensive buses in the end. Let's consider a simple numerical example. The linear program has this optimal solution. Now let's consider a different reality where the coefficients of the second variable are changed slightly, resulting in this linear program and its optimal solution. Clearly, the highest objective value is reached in the first scenario. It should also be noted that the optimal solutions are quite different in the two scenarios. Let's, for the sake of the example, say that x1 must be fixed in planning, but that x2 can be changed after we learn which of the two scenarios is the real one. This is referred to as a two-stage problem. More complex problems can of course have more stages and scenarios. In the example, let's say that the left scenario is the true scenario with probability 0.4, and that the right scenario is the true scenario with probability 0.6. Using stochastic programming with recourse, we can find the best solution on average that takes the two scenarios into account. The recourse action, of course, being the choice of x2, since we are allowed to change that after knowing which of the two scenarios is true. However, Before we do that, let's first look at what happens if we simply use the optimal solution from the first scenario in the second scenario. Since we get the best solution value in scenario 1, one could argue that it makes sense to just always use this solution. Then if scenario 1 is indeed the true scenario, we get lucky and get the highest possible solution value. However, if scenario 2 was the true scenario, we would have a solution value of 6.66, which is significantly lower than the 8 we could have gotten with the optimal solution for scenario 2. On average, if we simply use the optimal solution from scenario 1, we would get a solution value of 8.26. A similar calculation could be made using the optimal solution from scenario 2, but in this case we run into a problem. Due to the difference in the parameters of x2, the optimal solution to the second scenario is not even a feasible solution to the first scenario. Specifically, the third constraint is not satisfied, as illustrated here. We could fix this rather easily by using the recourse. If scenario 2 was the true one, we have no problem. And if scenario 1 was the true one, we could adjust the value of x2 to 1.5, which would satisfy the third constraint. In the end, this strategy would give a slightly better average objective value of 8.4. However, stochastic programming with recourse can improve the average objective value even further. To model the recourse action, the delayed choice of x2, we split x2 into two new variables, one for each of the two scenarios. We name these variables x21 and x22, x21 being the value of x2 in scenario 1 and x22 being the value of x2 in scenario 2. We can now update the objective function to equal the weighted average objective of the two scenarios. Notice that x21 is used in the part of the new objective corresponding to the objective of the first scenario, and x22 is used in the part corresponding to the second scenario. The appropriate probabilities of the scenarios are used to weigh the two parts of the new objective. The new objective can be reduced to this. We can now write the stochastic program with recourse as such. Notice how the second constraint, as well as the third constraint of the original problem, has been split into two, one for each of the two scenarios, using the appropriate version of the x2 variable. This ensures that the optimal solution will be feasible in both scenarios. But due to x2 being split in two, it is allowed to take on different values in the two scenarios. Using this technique, we have essentially modeled the recourse action directly in the linear program. The optimal solution to this model is x1 equal to 4, x21 equal to 3, and x22 equal to 4. And the optimal objective value is 44/5, which is equal to 8.8. If we compare this to the solution based on the optimal solutions from scenario 1 and 2, we find that the solution is quite different from those, and the average objective value is slightly better as well. For problems with many scenarios, the solution to the stochastic programming model with recourse can be much better than these other solutions, especially if the scenarios differ a lot, which was not really the case for this example. For more complex problems, it might also be cumbersome to even find solutions that are feasible in all of the scenarios. Stochastic programming helps here as well. Of course, an obvious trade-off is that the model can become large very fast if the problem has many scenarios or even multiple stages.